Welcome to Ask and Learn.
In this problem, we have A at a specified state contained in a piston-cylinder device, which undergoes an isothermal and then a constant volume process until it reaches a final temperature. So we wish to calculate the amount of heat transfer in this process and draw this process on a PV diagram as we've done here. So we see process 1-2 is the isothermal process in which the pressure decrease is associated with a volume increase, and process 2-3 is a constant volume pressure decrease. Now we make the assumption that A is an ideal gas here and that the kinetic and potential energy changes are negligible. Now the properties of A are its gas constant R, which is 0.287 kilopascal meter cube per kg Kelvin, and the specific heat at constant volume 0.718 kilojoule per kg Kelvin. Now 1-2, remember, is the isothermal process and 2-3 is the constant volume process. So this is our diagram. Our PV diagram is required. Now for our closed system, we can write the energy balance equation, E in minus E out is equal to the change in energy of the system, delta E. So this is a closed system because no mass crosses the boundaries of the system. Now, the net energy transfer is firstly due to the boundary work out of the system, and that's in process 1-2. That's negative since it's out of the system. And then we have heat coming into the system, so that's plus Q. And this is equal to the change in internal energy of the air, delta U. And delta U can be written as mCV times the change in temperature. The final temperature is T3 minus the initial temperature T1. So that's our energy balance equation, energy balance for the system. Now, to use this equation, we first need to find the mass of A. The mass of A, M, we get from the ideal gas relation P1 V1 over R T1. And these values are all known, so we can substitute them in. So the initial pressure is 600 kilopascals. The initial volume is 0.8 cubic meters. This is divided by the gas constant for A, 0.287, and that's kilopascals meter cubed per kg Kelvin times T1. Initial temperature in Kelvin is 1200. Hence we get the mass of A involved in this process to be 1.394, and that's kg. Now we also need to calculate the boundary work during process 1-2. Now this is an isothermal process, so this boundary work WB outwards in process 1-2 for an isothermal process is T1 times the natural log of the volume of state 2 over the volume of state 1. And this is also equal to T1 times the natural log of the pressure of state 1 over the pressure in state 2. So we can see that V2 over V1 is equal to P1 over P2. And this is true for any isothermal process. So we can substitute values into this equation, and we can find our boundary work done. So the mass of A is 1.394, that's in kg. The gas constant we said was 0.287. Remember, these values we got from our tables. And the temperature, initial temperature, T1 is 1200 Kelvin. Notice that we suppress the units here. Times a log of P1 over P2. So that's 600 kilopascals over the temperature in state 2, which is 300 kilopascals. And so if we perform this calculation, we get that the boundary work is 332.8 kilojoules. So now we have the boundary work for the system, and we can substitute the mass and the boundary work into the energy balance equation. So if we substitute in the energy balance equation, we can find the heat transfer. So the heat into this gas, into the system, is equal to the boundary work in process 1, 2 plus mCV times the change in temperature of the final state T3 minus the initial state T1. So this is equal to 332.8 kilojoules for process 1, 2 plus a mass of air of 1.394 kg times the specific heat of air 0.718 kilojoule per kg Kelvin times the change in temperature. Final temperature is 300 and the initial temperature is 1200, and that's Kelvin. And so we get the heat transfer into the system is minus 568 kilojoules. So what this means is that the net heat Q is out of the system and the heat transfer is 568 kilojoules.